So our next speaker is Sándor Kiss from Budapest, who will speak on generalized Sidon sets of perfect powers.
Thank you very much. So this is a joint work with Csaba Sándor. So, well, first of all, let me define the most important notions we are working with. So the first is the additive representation function. So consider a positive integer, which is at least 2, and a set, infinite set A of non-negative integers, and then RH A of n denotes the number of representations of a positive integer n as a sum of h distinct terms from the set A, and R star will denote the number of those representations of a positive integer n as the sum of h terms from the set A where equal terms are allowed. So the next important concept is the generalization of a Sidon set. So for a fixed positive integer g, a set of non-negative integers A is a BHG set if every positive integer n can be written as the sum of h terms from A at most g times where repetition are allowed. In the special case when g is equal to 1 and the number of terms is equal to 2, a B to 1 set is called a Sidon set. And really, so if g is 1, then this means that this representation function is at most 1, which means that every positive integer n can be written as the sum of 2 terms from the set A, which means that all the 2-term sums are different. So, and we will talk about a weak BHG set, which means that the other representation function is at most g for every positive integer n. And finally, I would like to define what is the basis of order h. So a set of non-negative integers is a basis of order h if every positive integer n can be represented as a sum of h terms from A where repetition are allowed as well. So let me tell you a few words about our motivation. So why and how we started this research. So at first I will show you some notation what I used, what we used. So I will denote n to the power of k is the set of non-negative k powers, and z plus to the power of k is the set of positive k powers. And A of n denotes the counting function of the set A, which means that this is the number of elements of the set A up to n. And I will use the usual asymptotic notation. F of x is double less than g of x, where f and g are 2 real valued functions, which means that f of x is equal to big O g of x. Now let me tell you what was the motivation of our research and how to start this research. So we studied some classical problems. So what is the first was the Waring problem, which asserts that for every k, the set of non-negative k powers is a basis of order m, where m is sufficiently large compared to the power of k. So there are several results about Waring problems, but the most interesting result is a theorem of Hardy and Littlewood. They gave an asymptotic estimation to the representation functions, so the number of representations of a positive integer n as the sum of k terms. And as you can see, the main term in their asymptotic estimations is n to the power of h over k minus 1, where h is large enough compared to k. So 2 questions arise here. So one is whether there exists a thin basis formed by k powers, which means that the representation function is positive but small, because it is easy to see from this theorem that the representation functions now is very large. And another question, which is more interesting for us, that whether there exists a basis formed by a sub-basis formed by k powers with a small density. So let's see what results exist in this direction. So many years ago, Choi, Erdős, and Nathanson proved that there exists a sub-basis of order 4 of non-zero of squares, such that the counting function is at most n to the power of 1/3 plus epsilon for any positive epsilon. And later, Zöllner improved their results. He extended the results to any age which is at least 4. So he proved that there is a sub-basis of order h of the squares such that the counting function is at most n to the power of 1 over h plus epsilon for any epsilon. And Wiersing sharpened the result of Zöllner by proving that there is a sub-basis of order h of squares such that the counting function is double less than n to the power of 1 over h times log n to the power of 1 over h. And it's easy to see that this is the best possible up to a log n term. And a natural question is, what can we tell about a higher exponent? So Nathanson proved that for any k which is at least 3, there is a subbasis of order h formed by k powers with density small o of n to the power of 1 over k. And he formulated a question in his paper. He asked what is the smallest density of the subbasis of order h formed by k powers where h is sufficiently large compared to k. And the natural question is if it could be n to the power of 1 over h plus epsilon, because this can be the best possible up to a epsilon term. And 20 years later, Wu affirmatively answered Nathanson's question. And Wu proved the existence of a basis formed by k powers of order h, such that the representation function is small. So he constructed a thin basis where the representation function is positive but small. And as a corollary, he got that the basis, what he constructed here is it has a small density. He proved that for any fixed k, there is a constant such that if m is large enough, then there exists a basis formed by k powers of order m, such that the counting function is double less than x to the power of 1 over m times logarithm of x to the power of 1 over m. And an easy observation shows that if we have a basis of order h, then it must have at least constant times x to the power of 1 over h elements, because the number of h tuples where the repetition are allowed is this binomial coefficient. And if we represent every positive integer, this is at least x plus 1, because there are x plus 1 integers up to x, and it's clearly less than a to the power a of x to the power of h. And this gives that the basis cannot have a small number of elements. And so in the other direction, there is a natural question that what can we tell in the other direction? So we studied the following question, which is a complementary question in some sense, that what can we tell about BHG sets? Because we know that the BHG set cannot be too dense. So our question was, does there exist a BHG set formed by k powers such that its density is as large as possible? But what does it mean? What does it mean as large as possible? It is easy to see that the counting function of a set formed by k powers is at most x to the power of 1 over k. This is clear. And anyway, there is an estimation, trivial estimation of the number of elements of a BHG set, because there are at most a of x plus h minus 1 choose a numbers that can be represented as the sum of h terms up to h x. And this is clearly at least h a of x to the power of h over h factorial. And and R star is bounded by g. If we have a BHG set, then we get that by using the trivial estimation, what I told you, that a of x is double less than x to the power of minimum 1 over k and 1 over h. But it turned out that this can be improved a little bit. So if we consider this quantity, which is the number of positive integers up to x that can be represented as the sum of two non-zero squared, then a well-known theorem of Landau states that n of x is asymptotically constant times x over square root of log x, where c here is the well-known Landau-Ramanujan constant. So by using this theorem and trivial estimation to the number of the number of elements of the set and that can be written as the sum of the two squares. So we get that the counting function of such a set is double less than x to the power of 1/2 minus epsilon. So these simple observations made us to formulate the following conjecture. So we conjecture that for every k, which is at least 1, and h, which is at least 2, and for any positive epsilon, there exists a BHG set formed by positive k powers, which is very dense. In particular, the counting function is at least constant times x to the power of the minimum of 1 over k and 1 over h minus epsilon. So our long-term aim is to prove this conjecture, but first let's see what known results exist about this conjecture. So the simplest case, when k is equal to 1, this is a classical result of Erdős and Rényi, that there exists a B2G set formed by positive integers. And later we extended the results by proving that there exists a BHG set formed by positive integers. So we have a probabilistic proof as well. The idea of the proof appeared in Wu's paper as well, but there is a nice direct construction by using the idea of Ruzsa, which is based on the number systems with a variable base. And what's happening when we increasing the exponent k, then Sillervello proved that for any positive integer g and positive epsilon, there is a B2G set of squares such that its representation function is at least constant times x to the 1/2 minus epsilon. And this theorem implies our conjecture when h and k are both equal to 2. So both the exponent and the number of terms are equal to 2. And there is another conjecture of Lander and Parkin. They considered this Diophantine equation, which is the sum of n k powers is equal to the sum of m k powers. And if it has a non-trivial, they conjecture if it has a non-trivial solution, then the number of unknowns is as large as at least as large as the exponent. And this conjecture would imply our conjecture when the number of terms is smaller than k/2. So trivial observation that if our conjecture is true, when the number of terms h is equal to the exponent k, then it also holds when the number of terms h is at most as large as the exponent k. And let's see what can we, so I talked about squares, and let's see what can we tell about cubes. There is a well-known theorem which states that the number of representations of a positive integer, the sum of two cubes, can be made arbitrarily large. And this implies that the cubes do not form a B2G set for any g. And if we increase the exponent, then what can we tell about the quartics? There is a nice theorem of Swinerton-Dyer, which states that given any real solution of this equation, a to the power of 4 plus b to the power of 4 is equal to c to the power of 4 plus d to the power of 4, then we can find a rational solution as close as we is to it. And this implies that the quartics don't form a Sidon set, but it may happen that they form a B2 set. And finally, it is conjectured that the fifth powers form a Sidon set. But this conjecture is still open and seems difficult. But there is another conjecture which is called hypothesis K, and this is due to Hardy and Littlewood, and this states that the number of representations as the kth distinct positive kth powers of a positive integer n is bounded by constant times n to the power of epsilon. And it's well known that this hypothesis K is true when k is equal to 2. So for the squares, 2 term squares is true. But for k is equal to 3, Mahler disproved this conjecture. He proved that for infinitely many n, the number of representations as the sum of 3 positive cubes is bigger than constant times n to the 1 to the power of 1 over 12. And the conjecture, this hypothesis K is still open when k is at least 4. And now let's see what we could prove. So we could prove that if this hypothesis K holds, then there exists a set of positive kth powers such that it is a weak BHG set, so the representation function is bounded, is as dense as in our conjecture. So in particular, we can prove that if k is a positive integer and h is between 2 and k, and for every eta positive number, there is a positive integer such that for every large enough n, if this number of h distinct representations of distinct positive kth powers of n is less than n to the power of eta, then for every positive epsilon, there is a weak HG set formed by positive k powers, which is as dense as possible. And as a corollary, we get that there exists for every k, which is at least 2, and for every positive epsilon, there exists a B2G set formed by positive k powers such that it is as dense as possible. And on the other hand, we can prove the following theorem, but before I state the theorem, I would like to tell you a problem. We don't even know what's happening when the number of terms is 3. So we don't know if there exists a set of non-zero squares such that the 3 terms representation function is bounded and this set is as dense as possible. So what we can prove that for every positive integer, which is at least 2, there is a positive integer such that if age is at least age naught, and then for every positive epsilon, there is a set formed by positive k powers such that this is a weak BHG set. So this representation function is bounded, and this is as dense as possible. So the counting function is at least constant times x to the power of 1 over age minus epsilon. So we can see here age is large enough compared to the exponent k. Now let me tell you a few words about the proof. So the proof of this theorem. So to prove the existence of such sets directly is very difficult or hopeless. That's why we use the probabilistic method to do this. And let me tell a few words about the philosophy of the probabilistic method. So we would like to prove that a set exists with some properties, and then it is enough to prove that a properly defined random set satisfies this required property with positive probability. And how to do this? This in general requires that some relations in connection to this property, which depends on n, holds. But we prove that this relation fails with small probability. And if this probability is small enough such that the corresponding infinite series converges, then this relation holds with probability 1 for every large enough n. And then we can apply the Borel-Cantelli lemma, because this infinite series is converges, and this is a well-known lemma. But to do this machinery, we need a valid probability space. So if we denote by omega the set of strictly increasing sequences of positive integers, then this lemma due to Erdős and Rényi shows that this valid probability space exists. So if we have real numbers between 0 and 1, and then there exists a probability space such that these events, that A is in omega, the sets of A is in omega and N is in A, they are measurable, and they measure is alpha n, and these events are independent. Now, how to use the probabilistic method here? We have to create a random variable from our representation function, and we do this in the following way. So we can define, if you have a set A, we can define the indicator random variable, which we denote by rho A n. And then in this case, it is easy to see that the representation function is equal to the sum of the product of these random variables. So representation function is the sum of indicator random variables. And the little difficulty arises here, because if age is bigger than 2, these random variables in these sums are not independent, because the same row may appear in many terms. And of course, the counting function can be written as a sum of indicator random variables as well. So, and there is a nice combinatorial tool that we use in our proof. And this is the so-called sunflower lemma or data system lemma. So a collection of sets, assume that we have R sets, they form a delta system or a sunflower if the sets have pairwise the same intersection. And there is a nice statement of Erdős and Rado. So if we have a system of sets of each sets of size k, and it is large enough in the sense that there we have at least or more than r minus 1 to the power of k times k factorial sets in our system, then this set system contains R sets which form this delta system configuration. Okay, so how to use this delta system configuration in our case? So if we have a representation of a positive integer n as a sum of h terms, then we can assign a set of these representations. We can put the terms of the representations in a set. So if we have a positive integer with a lot of representations, then it means that we have a lot of sets formed by the terms of each representations. So you can imagine, if you look at my small picture, so this is a delta system. So say here you see 5 element sets, and this is the core of the delta system, these 2 elements, and these are the petals which contains 3 elements. And if we have this delta system assigned to the representation function, so we have a representation functions of n as the sum of 5 terms, then if we subtract these terms from in the core, then we get n minus these 2 terms as the representation as the sum of 3 elements. But these 3 element representations, so these representations in the petals are disjoint. So this is what we apply. And let me tell you a few words about the proof in the remaining 1 minute. So we define a random set in this way. So 0, the probability of n in A is 0 if n is not a kth power, but 1 over n to the power of 1 over k minus 1 over h plus epsilon if n is a positive kth power. And in the first step, we estimate the expectation of the L terms representations of n, where L is between 2 and h. So this requires a complicated computation, as we use a lemma which is based on the application of the circle method. And after that, we use the delta system lemma that we prove that with probability 1, the h terms representation is bounded. So here we use the Erdős-Tatalis method. We consider the maximum number of disjoint representations as the sum of L terms of a positive integer n, and then we apply the delta system lemma. We estimate this quantity and apply the delta system lemma to get that this representation function is bounded. And finally, by using a variant of Chernoff inequality, we can estimate our counting function that it is at least constant times 1 x to the power of 1 over h minus epsilon. Okay, so that's all I wanted to tell you today. So thank you very much for your attention.
Thank you very much. I know, are there any questions? I am looking. Trevor Woolley had made a comment in the chat at some point, but.
Okay.
All right, well, oh, wait, Q&A.
Yeah, okay. Okay, thank you, your remark, okay. Okay.
All right, well.
Thank you very much, your remark, yeah.
Yeah. Well, so if there are not questions, again, I thank the speaker, and we will resume in 5 minutes. Thank you, Sándor.
Yeah, my pleasure.